Section 1 Introduction. We're here to discuss large language models, LLMs, which have been game changers in the field of natural language processing and have significantly improved chatbot systems. However, these models have a downside. They're slow when it comes to inference, which can be a problem for real-time interactions. For instance, the Claude model, which is accessed through Slack, takes 22 seconds to respond to a question, while the Vicuña 33BV 1.3 model, which is based on a 33 billion parameter llama model and runs on a single NVIDIA A100 GPU, takes 43 seconds. We've identified three main reasons for this slow inference. First, these models are large and require a lot of memory and computational power. For example, the GPT-3 model with 175 billion parameters in FP16 format needs 350 gigabytes of memory, which is equivalent to the memory of 5 A100 GPUs, just for inference. Even if you have enough GPUs, the heavy memory usage and computation can slow down the inference process. Second, the core attention operation in the popular transformer architecture is input-output bound and has a quadratic memory and computation complexity based on sequence length. Third, the sequential decoding approach used in inference generates tokens one by one, where each token depends on the previous ones. This method introduces significant latency because the generation of tokens can't be done in parallel. There's a lot of research addressing the first two issues, focusing on reducing the model size and improving the attention operation. These studies usually involve compressing or redesigning the model, or redesigning the system and hardware. However, we're taking a different approach and focusing on the third issue. We're challenging the assumption that LLMs must use sequential decoding. We've found that it's possible to use parallel decoding with existing LLMs without changing their model, system, or hardware. For example, we've managed to reduce the latency from 22 seconds to 12 seconds with the Claude model, and from 43 seconds to 16 seconds with the Vicuña 33BV 1.3 model. Our approach is inspired by how humans answer questions. We don't always think about questions and write answers sequentially. Often, we first come up with a basic structure or skeleton of our answer, and then fill in the details. We wondered if we could get LLMs to do the same thing. So, we developed a method called skeleton of thought, SOT. The idea is to guide the LLM to come up with a skeleton of the answer first, and then fill in the details in parallel. This method can be used to speed up both open-source models with batch decoding and closed-source models with parallel API calls. We tested SOT on 11 recently released LLMs and found that it not only speeds up the process, up to 2.39 times faster, but it can also improve the quality of the answers in terms of diversity and relevance. However, this approach raises more questions than it answers. For example, the human thinking process is more complex than SOT. It involves many steps structured in a complex graph. Could we and should we organize the LLM's thinking and writing process as a graph of thought? This could potentially combine the benefits of SOT on efficiency and global understanding with the benefits of chain of thoughts, COT, on logical reasoning and impromptu thinking. Another point to consider is that the field of machine learning is moving from a model-centric era to a data-centric era. It's becoming more important to design the data pipeline to guide learning than to design the model structure to improve the model quality. However, when it comes to improving model efficiency, most of the previous work is still model-centric. SOT is a first attempt at data-centric optimization for efficiency, as it guides LLM to organize its output during inference to improve efficiency. We're excited about the potential of this approach and will share more insights and knowledge on the positioning and outlooks of SOT in the future. Section Summary. Large language models, LLMs, have shown impressive performance in natural language processing but suffer from slow inference times. This is due to factors such as large model sizes, attention operation complexity, and sequential decoding. In this paper, we propose skeleton of thought, SOT, a method that allows LLMs to derive a skeleton first and then complete each point in parallel, resulting in significant speedups and improved answer quality. This data-centric optimization approach opens up new possibilities for organizing LLM's thinking process and has the potential to combine efficiency with logical reasoning. Section 2 Skeleton of Thought, SOT. The section we're discussing is titled Skeleton of Thought, SOT, and it's about a method that SOT uses to generate answers to user questions. Firstly, SOT creates a basic structure or skeleton for the answer. It does this by using a template, which we'll call T-S, and the user's question, Q, as input. This template is designed to guide the language model, or LLM, to produce a brief outline of the answer. From this outline, we then extract key points, which we'll refer to as B points. Next, we move on to the point expanding stage. Here, the LLM elaborates on each of the B points, one by one. For each point, SOT uses another template, T-pay, which includes the user's question, the skeleton of the answer, the index of the point, and the skeleton of the point. This template guides the LLM to expand on the point. Once all the points have been expanded, we combine them to form the final answer. The skeleton template, T-S, is designed to produce a short, consistent output that's easy to extract points from. It does this by clearly defining the task, providing two simple examples, and starting off the answer with 1. Quote. We've found that this usually results in the desired format, so we can use a regular expression to extract the point indexes and skeletons from the response. The point expanding template, T-pay, describes the task of expanding on a point and provides a partial answer. We also include instructions to keep the answer brief, usually in 1 or 2 sentences. Unlike the skeleton template, we've found that examples aren't necessary to get good results. For models that only have API access, we can make multiple API calls at the same time to expand on the points. For open source models, we process the point expanding requests as a batch, adding padding to the left of the requests. For more details on how this is implemented, please refer to the original text. Section summary. The skeleton of thought, SOT, method consists of 2 stages, the skeleton stage and the point expanding stage. In the skeleton stage, SOT uses a prompt template to guide the language model, LLM, to generate a concise skeleton of the answer. Then, in the point expanding stage, the LLM expands on each point in parallel using a point expanding prompt template. The final answer is obtained by concatenating the point expanding responses. Section 2.2 Why SOT reduces decoding latency. Let's delve into why the skeleton over tree, SOT, method can significantly speed up the process. We'll focus on the point expanding stage for now, and discuss the skeleton stage's overhead later. In API-based models, the traditional method sends one API request at a time to the server. In contrast, SOT sends multiple API requests simultaneously to gather different parts of the answers. We've noticed that the latency of the APIs we use is directly related to the number of tokens in the response. If the number of requests doesn't exceed the rate limit, SOT can speed up the process. In open source models, the traditional method processes one question at a time and decodes the answers in sequence. On the other hand, SOT processes multiple point expanding requests and decodes the answers in a batch. We're interested in understanding how much additional memory overhead and latency would be caused by processing a batch of sequences instead of just one. A typical language model, LLM, generative process has 2 phases: the prefilling phase, where the prompt is parsed to create a key value cache for later use, and the decoding phase, where tokens are generated one by one sequentially. The decoding phase is the main contributor to the overall latency, especially when generating a long response. When we ran Vicuña 7B on NVIDIA A180G, we found that the actual computing performance during the decoding phase was only 0.31 teraflops, 0.1% utilization, compared to 40 teraflops, 12.8% utilization, during prefilling. This discrepancy is due to the fact that all LLM weights need to be loaded onto the GPU chip at least once for decoding one token, causing a bottleneck in the decoding process. When we use batch decoding, the latency of decoding one token for each sequence remains roughly the same as the batch size increases. This is because the amount of LLM weights that need to be loaded onto the chip doesn't change. As a result, the GPU computation utilization increases almost linearly as the batch size increases. In simpler terms, if we divide the final answer of length n into B segments of length n, B, and decode them as a batch, we can achieve a B times decoding speedup compared to sequential decoding. However, in practice, the actual speedup is less than B due to overhead from prefilling longer requests and potential imbalances in the lengths of the B segments. Regarding peak memory overhead, the amount of LLM weights can be significantly larger than that of all the intermediate activations, especially if the prefilling token length isn't too large. Therefore, the LLM weights make up the majority of the memory footprint in our test cases. As the batch size increases, the peak memory overhead due to the increasing size of the key value cache and activation grows slowly. In all our experiments, we were able to run SOT on a single GPU without needing to use other peak memory optimization techniques, such as quantization or offloading. This was possible thanks to the small peak memory overhead. Section summary. The section 2.2 explains why SOT, skeletons over templates, can significantly reduce decoding latency. SOT achieves this by sending multiple API requests in parallel to get different parts of answers, leading to a speedup. Additionally, SOT processes multiple point expanding requests and the answers in a batch, resulting in increased GPU computation utilization and a B times decoding speedup compared to sequential decoding. The peak memory overhead is also minimal, allowing SOT to run efficiently on a single GPU without the need for additional memory optimization techniques. Section 3. Experimental results. In our experiments, we used the Vicuña 80 dataset, which includes 80 questions across 9 different categories such as coding, math, writing, roleplay, and others. We tested our method, known as SOT, on 11 recently developed models. These models include 9 that are open source and 2 that are API-based. We obtained the weights for all the open source models from Hugging Face. We evaluated the efficiency of these models in 2 ways. For the API-based models, we measured the time it took for each API call and added the time taken by the skeleton API call and the slowest point expanding API call to get the total SOT latency. For the open source models, we focused on those based on the Llama 7B, 13B, or 33B architectures. To facilitate quick analysis, we created a latency profiling table for each Llama architecture on the NVIDIA A100. This table includes the time it takes to prefill sequences of varying lengths with different batch sizes, and the time it takes to decode one token with a context of varying lengths with different batch sizes. Using these tables, we can quickly estimate the SOT latency for a given number of points and token lengths of the skeleton request, skeleton response, point expanding request, and point expanding response. We also conducted experiments on the NVIDIA RTX 3090 for the 3.7B open source models, namely Llama 2 Chat 7B, Vicuña 7B v1.1, and Vicuña 7B v1.3. We compared the actual latency of SOT and normal sequential generation, and found that SOT reduces the end-to-end latency on different models. On average, SOT achieved more than twice the speed on 6 out of 11 models, and a speedup of more than 1.8 times on 3 other models. However, SOT did not speed up the STABLEVICUNA13B model. We also found that the speedups were slightly higher when we excluded the math and code question categories, which are not suitable for the current version of SOT. In terms of the number of points, Llama 2, Vicuña 7B v1.1, Vicuña 7B v1.3, and ChatGPT 3.5 generated fewer points, while STABLEVICUNA13B generated the most points on average. We also found that STABLEVICUNA13B tends to produce shorter normal answers, and its longest point expanding responses for many question categories can be as lengthy as the overall normal answer. This is because STABLEVICUNA13B does not follow the "write it very shortly" instruction in the point expanding request, which is why SOT cannot accelerate it well. On the other hand, ChatGPT 3.5 and Claude follow the point expanding request better and generate shorter point expanding responses than other open source models. They also generate more balanced point expanding responses. Finally, we found that using SOT on most models results in an average answer length that is about 1 to 2 times longer. However, using SOT on STABLEVICUNA13B results in a significantly increased final answer length due to its large number of points and long point expanding responses. Section Summary. The experimental results section presents the datasets used and the models tested in the study. The efficiency of the models is evaluated by measuring the latency of API-based models and creating latency profiling tables for open source models. The study shows that the current solution achieves a speedup of over 2 times on 6 out of 11 models, with the highest speedup observed on ChatGPT 3.5 and Vicuña 7B v1.3. However, the current solution does not significantly accelerate STABLEVICUNA13B due to its failure to adhere to the point expanding request. Additionally, using SOT on most models results in an average answer length that is 1 to 2 times longer, while using SOT on STABLEVICUNA13B significantly increases the final answer length. Section 3.1.2 Speedup Breakdown, Question Categories. In this section, we delve into how the speed of thought, SOT, method reduces the time it takes to answer different types of questions. We calculate the average time reduction for each type of question across all models. We've highlighted the types of questions for which SOT can provide high-quality answers in green, and the rest in red. It's clear that SOT can already speed up the response time for all types of questions. For the 5 types of questions where SOT can provide high-quality answers, knowledge, common sense, generic, roleplay, counterfactual, SOT can speed up the answer generation process by 1.95 to 2.27 times. Next, we look at the time it takes for SOT to generate answers compared to the normal method. We find that the decoding phases are the main contributors to the total time it takes to generate an answer. Even though SOT takes longer to prefill in the skeleton stage than the normal method and introduces additional time for point-expanding prefilling, this has a negligible impact on the total time and therefore the speed increase. To compare the quality of the answers generated by the normal method and SOT, we use two evaluation frameworks based on language model metrics, LLM, FastChat and LLM-Zoo. We present a question and a pair of answers, one from the normal method and one from SOT, to an LLM judge, ChatGPT-3.5 in this case, and ask it to choose its preferred answer. The judge can decide that SOT's answer is better, the same, or worse than the normal answer. Here are more details about how we evaluate the quality of the answers. 1. FastChat provides a metric for the overall quality of the answers. LLM-Zoo, on the other hand, provides 5 detailed metrics on the answer's coherence, diversity, immersion, integrity, and relevance. 2. FastChat provides 2 special prompts for coding and math questions for a more accurate evaluation, whereas LLM-Zoo does not. Following LLM-Zoo's implementation, we exclude math and coding questions from all LLM-Zoo evaluation results. 3. To avoid bias from the order in which the 2 answers are presented to the LLM judge, we run the evaluation twice, changing the order of the answers each time. In each evaluation, a score of 1, 0, or -1 is assigned when SOT's answer is better, the same, or worse, respectively. The final evaluation is that SOT's answer is better, the same, or worse when the sum of the 2 scores is positive, 0, or negative. For example, if SOT's answer is better in one evaluation and worse in the other, the result is a tie. If SOT's answer is better, or worse, in one evaluation and the same in the other, the result is a win, or loss. We first present the overall quality of SOT's answers, and then delve into the details across different types of questions, models, and metrics. Section Summary. The section discusses the speed-up breakdown of the SOT model for different question categories, showing that SOT can provide high-quality answers and speed up the answer generation process by 1.95 to 2.27 times. It also analyzes the latency breakdown of SOT and normal generation, highlighting that decoding phases contribute the most to the overall latency. The evaluation of answer quality is conducted using FastChat and LLM-Zoo frameworks, considering metrics such as coherence, diversity, immersion, integrity, and relevance. The evaluation is done twice to avoid bias, and the final result is determined based on the sum of scores. Section 3.2.1 Overall Quality. In Section 3.2.1, we discuss the overall quality of our model, SOT, compared to the standard generation method. We use 2 metrics from FastChat and LLM-Zoo to evaluate the quality of the answers. We found that there's a significant difference between the 2 metrics when it comes to determining when SOT outperforms the baseline, 49.0% versus 10.4%. However, both metrics agree that SOT performs at least as well as the baseline in over 76% of cases. When we exclude math and coding questions, which SOT isn't designed to handle, SOT performs at least as well as the baseline in over 90% of cases. This suggests that SOT's answers are generally of good quality. In Section 3.2.2, we break down the quality of SOT's performance across different question categories. We calculate the net win rates, the win rates minus the lose rates, for all question categories. We found that LLM-Zoo tends to be more optimistic about SOT's quality than FastChat. However, both agree that SOT performs well on generic, common sense, knowledge, roleplay, and counterfactual questions, but struggles with writing, Fermi, math, and coding questions. We found that math questions are challenging for SOT because they require sequential thinking. SOT struggles to come up with a solution plan and then deduce each step independently without referring to previous results. For example, in a math problem, ChatGPT 3.5 was able to correctly outline the solution steps but made mistakes in the second step because it didn't know the results from the first step. Fermi questions, like math questions, require step-by-step thinking. For instance, to answer a question about the number of times the Earth has orbited the Sun since the beginning of life, the model needs to make assumptions about when life began on Earth. In this case, ChatGPT 3.5 made a mistake in its calculations because it didn't know that it had already assumed 3.5 billion years in a previous step. Coding questions also pose a challenge for SOT. While the models can usually break down the coding problem into smaller tasks, the quality of the generation during the point-expanding section summary. Section 3.2.3 Quality Breakdown, Models. We're now going to delve into how the skeleton over text, SOT, method performs on various models. We've calculated the net win rates for all models and found that while the two general metrics from FastChat and LLM have different absolute values, they rank the models similarly. Specifically, both metrics agree that OpenChat-13b, Vicuña 7b v1.1, Claude, and ChatGPT 3.5 have low net win rates, while Vicuña 13b v1.3, STABLEVICUNA 13b, and ULTRALM 13b have high net win rates. We've analyzed the responses and summarized our findings below. Models with low net win rates. We've noticed two main reasons for the low net win rates. Firstly, weaker models like OpenChat-13b and Vicuña 7b v1.1 struggle to accurately follow the sought prompts. For instance, OpenChat-13b sometimes includes unwanted content in the skeleton, such as completing the skeleton points as shown below. For example, when asked to explain how many lightning strikes occur on Earth each day, OpenChat-13b's response included unnecessary details about the Earth's atmosphere and lightning formation, rather than focusing on the calculation of lightning strikes. Similarly, both OpenChat-13b and Vicuña 7b v1.1 sometimes fail to provide any details during the point expanding stage when they are needed. For instance, when asked to explain a superhero's origin story to a child, Vicuña 7b v1.1 feat's response lacked detail. These issues contribute to their poor net win rates. Secondly, stronger models like Claude and ChatGPT 3.5 don't have major issues with SOT's answers except for the common issues across all models. We believe their low net win rates are mainly because their regular sequential generation is already quite good. Models with high net win rates. The models with high net win rates, namely Vicuña 13b v1.3, STABLEVICUNA 13b, and ULTRALM 13b, fall between the two extremes mentioned above. They are competent enough to understand SOT prompts, and while they sometimes have the same issues as OpenChat 13b and Vicuña 7b v1.1, these problems occur less frequently. Additionally, their regular sequential generation performance has more room for improvement than Claude and ChatGPT 3.5, making the benefits from SOT more noticeable on these models. In summary, SOT doesn't work well for some models that struggle to understand the skeleton and point expanding prompts. However, for models that can understand the SOT prompts, the quality of answers might improve. We anticipate that further refining SOT prompts or fine-tuning the models could make it easier for language models to understand the skeleton and point expanding prompts, ultimately leading to better answer quality. Section summary. The performance of the SOT, skeleton-to-text, model is evaluated on different models, and it is found that models like OpenChat-13b and Vicuña 7b v1.1 have low net win rates due to their inability to precisely follow the SOT prompts. On the other hand, models like Vicuña 13b v1.3, STABLEVICUNA 13b, and ULTRALM 13b have high net win rates as they are able to understand the prompts better. However, further improvements in the SOT prompts or fine-tuning of the models are expected to enhance the answer quality. Section 3.2.4 Quality Breakdown, Metrics. In this section, we delve into the quality breakdown of the metrics used in our evaluations. We've previously focused on general quality metrics for the answers provided by our system. Here, we'll use more detailed metrics from LLMs to highlight the areas where our system, known as SOT, can enhance or potentially diminish the quality of the answers. On average, we've found that SOT enhances the diversity and relevance of the answers, but it can negatively impact the immersion and coherence of the responses. We've analyzed the answers and summarized our findings below. First, let's look at metrics where SOT didn't perform as well. 1. Coherence. In the LLMs evaluation, coherence is described as the logical flow of the response from one point to the next, making it easy to read and understand without major gaps or inconsistencies. The more coherent the response, the better. SOT's answers are structured as a list of points, which works well for some questions but not all. For instance, in questions that require a passage, email, or script, the introduction and conclusion paragraphs are often missing, and the answers usually lack transition sentences between consecutive points. This makes the answers less coherent. For example, when asked to write a script for a YouTube video exploring the history and cultural significance of jazz, SOT's answer was a list of points about jazz history. While the content was good, it lacked the flow and coherence needed for a YouTube script. 2. Immersion. In the LLMs evaluation, immersion is described as the response acting like the assigned role using the tone, manner, and vocabulary the role would use. The more assistant-like tones, the worse. The more in character, the better. The way SOT breaks the answers into a list makes its answer less in character, resulting in a lower immersion score. For instance, when asked to pretend to be a world-famous chef describing a signature dish to a panel of judges, SOT's answer was a list of points about the dish. While the answer covered sufficient aspects and details, it lacked the casual, conversational tone expected from a chef. Now, let's look at metrics where SOT performed well. 1. Diversity. In the LLM Zoo evaluation, diversity is described as the response being comprehensive and providing a range of information that is not limited to a single perspective. The more perspectives, the better. The skeleton stage in SOT encourages the system to think from multiple perspectives, resulting in answers with better diversity. For example, when asked how to determine if a person is genuinely interested in a conversation or simply being polite, SOT's answer covered 5 aspects, whereas the normal answer only mentioned 1 aspect. 2. Relevance. In the LLM Zoo evaluation, relevance is described as the response being closely related to the question and answering the question accurately with sufficient details without repetition or redundancy. The more relevant, the better. In the skeleton stage, the system is forced to propose several points around the question, and in the point-expanding stage, the system is required to only discuss these points. This results in answers from SOT having better relevance. For instance, when asked why some people enjoy the sensation of being scared, such as by watching horror movies or going on roller coasters, while others avoid these experiences, SOT's answer was well structured into 5 reasons with sufficient explanations, and it did not waste space in irrelevant contents. In summary, SOT encourages the system to directly discuss the answers from multiple aspects without filler words. This improves the diversity and relevance of the answers with a loss of coherence and immersion. However, even for coherence and immersion, SOT is not worse than the normal generation around 60% of the time. One future direction is to improve the SOT prompts so that the answers can be better in more metrics. Section Summary. The quality breakdown of the SOT system reveals that it improves the diversity and relevance of answers while sacrificing coherence and immersion. The answers generated by SOT tend to cover multiple perspectives and stay closely related to the question, but they may lack smooth transitions and in-character tones. However, it is worth noting that SOT performs better than the normal generation in terms of coherence and immersion around 60% of the time. Future improvements could focus on enhancing the prompts to further enhance the quality of the answers. Section 4. In the context of literature. In this section, we aim to place our method, SOT, within the broader landscape of current research. We will discuss how SOT relates to, differs from, and can leverage other existing methods. 4.1 Improving Large Language Models, LLMs. A significant amount of research has been devoted to improving the speed and efficiency of LLM training and inference. Firstly, we'll talk about techniques that compress the model, reducing its complexity. These methods alter the model and can potentially improve both speed and efficiency, although there's a risk of reducing the model's quality. Next, we'll discuss system-level strategies that optimize the computational graph or manage the allocation and scheduling of the computational graph on computational and storage devices. Current solutions for LLMs primarily focus on speeding up the prefilling phase or enhancing the training speed. Lastly, for scenarios where inference latency is a priority, we'll present existing methods that speed up the decoding phase. Model-level optimization. Efforts have been made to tackle the quadratic complexity of basic attention by creating new attention mechanisms. However, these methods often require substantial retraining. Model compression techniques have been used to lessen the workload of LLMs. Approaches such as quantization, static or dynamic pruning of weights, activation, and attention are popular for compressing LLMs, as they only require a small amount of fine-tuning to maintain the original algorithm's performance. When we look at the broader field of model compression, we see that model co-design or compression for efficiency has gained a lot of attention in recent years and has expanded into large research fields like pruning, quantization, factorization, and neural architecture search. SOT differs from the model co-design approach. It falls under the content co-organization for efficiency paradigm, aiming to improve LLM efficiency. As we transition from a model-centric era to a data-centric one, and as AI becomes more adept at understanding and generating longer sequences, the co-organization of content for efficiency could become a crucial tool in the efficient LLM toolkit. Section Summary. In this section, the authors position the concept of SOT, summarization of transformers, within the current research ecosystem. They discuss how SOT is connected to and different from other methods, as well as how it can harness the power of these methods. They also highlight the importance of efficient LLMs, language models, and discuss model-level compression techniques that reduce model complexity, system-level efforts that optimize computational graph assignment and scheduling, and existing methods that accelerate the decoding phase. They emphasize that while model compression has received significant attention, SOT focuses on content co-organization for efficiency, which may become an important tool in the efficient LLM toolbox as we move towards the data-centric era. Section: System-level optimization. We've been working hard to optimize systems for lossless acceleration, particularly focusing on the I/O-bound nature of large language models, LLMs, on modern hardware platforms. A lot of research has been done on modifying the computational graph to make it more I/O friendly. This involves combining and executing operations in a way that is more compatible with I/O. Take flash attention as an example. It combines all operations of one attention into one GPU kernel. This is done using spatially tiled computation, which helps to reduce the off-chip I/O of the attention map. Flash attention is great for speeding up training and the prefilling phase of inference. However, it doesn't do much for the decoding phase, especially when the batch size is small. This is because the decoding phase is slowed down by the I/O of weights, not the activation or attention map. For instance, when the context length is 64, decoding one token using Llama 7B requires loading each of the 7 billion parameters from the off-chip high-bandwidth memory, HBM, onto the GPU chip at least once. But only about 20 million, 0.02 billion, activation values need to be transferred between the off-chip HBM and GPU chip. There have been various techniques proposed to maximize the throughput of LLM training or batched inference. These techniques optimize the division, assignment, and scheduling of computations, storage, and communications on devices, given the computational graph and the device configurations. Serving systems, which aim to meet service-level objectives, focus on improving the serving throughput under latency constraints. They do this by packing multiple queries together into a batch to improve hardware utilization. This batching technique has been very effective in increasing throughput, leading to the development of various versions. Some research has focused on deciding which queries to batch together, while others selectively batch parts of the model to enable fine-grained iteration-level batching or multitask batching. However, these system-level techniques are mainly beneficial for throughput-oriented scenarios like training and batched inference. They don't do much to optimize the end-to-end decoding latency in inference. But that's where SOT comes in. SOT can use these throughput-oriented techniques to help with the end-to-end latency. It does this by decoding multiple segments in parallel and then combining them. This can improve the throughput of the batch decoding of multiple segments. For example, we can use FlexGen to enable high-throughput batch decoding on relatively low-end GPUs. SOT also guides the LLM to adjust the sequential workload to be parallelizable between contents. This is different from previous parallelism levels, which include inter-instance, inter-operation, intra-operation, and inter-token. Section summary. System-level optimization techniques have been developed to address the I/O-bound nature of large language models, LLMs, on modern hardware platforms. These techniques focus on adjusting the computational graph, optimizing computations, storage, and communications on devices, and utilizing batching techniques to improve throughput. However, these techniques are mainly effective for training and batched inference scenarios and do not effectively optimize the end-to-end decoding latency in inference. The proposed segment-level optimization technique, SOT, parallelly decodes multiple segments and aggregates them afterward, utilizing these system-level techniques to improve the throughput of batch decoding and adjust the workload to be inter-content, parallelizable. Section: Acceleration for latency-oriented scenarios. We're focusing on improving speed in situations where latency is a critical factor. The main issue in these scenarios is the autoregressive decoding phase, which is where tokens are produced one at a time. Because these tokens are interdependent, we can't compute them simultaneously, which means we're not making full use of the GPU's capabilities. To speed up the decoding process, speculative decoding methods have been proposed. These methods use a simpler approach to create a preliminary sequence of tokens, using a smaller assisting model. The larger language model, LLM, then checks the sequence in parallel, keeping the part of the sequence that matches its own results. The process is slowed down by the need to input and output the model's weights, and because we're not fully using the computational units. However, checking multiple tokens at once takes about the same amount of time as generating a single token. So, the longer the matching sequence, the faster these methods can work. A recent study suggested using a group of assisting models to create a tree of potential token sequences, rather than just one. This allows us to generate multiple tokens in different segments at the same time. In recent years, a new approach has emerged for LLMs, which involves designing prompts that include task descriptions, and possibly a few examples. This helps guide the LLM in generating answers for a variety of tasks. Researchers have found that LLMs that have been tuned using instructions are very good at generalizing to new tasks, thanks to the variety of natural language descriptions they encounter during the tuning process. They can also learn in context using a few examples, without needing to adjust the weights. Because of these abilities, researchers have been manually creating, automatically searching for, or continuously adjusting the prompts to reveal the LLM's capabilities for different tasks. For instance, the chain of thought prompts significantly improve performance on tasks that require logical thinking and reasoning, by providing a "let's think step by step" instruction or a few examples. Hugging GPT designs prompts to guide the LLM in generating structured JSON for the coordination of multi-model execution to complete complex tasks. There's a large body of research on prompting methods, all aimed at revealing different capabilities of LLM and improving the quality of answers for different tasks. In contrast, our approach, which we call SOT, uses the power of prompting to improve efficiency. Section summary. In latency-oriented scenarios, the bottleneck for end-to-end latency lies in the autoregressive decoding phase, where tokens must be generated one by one, causing underutilization of the GPU. Speculative decoding methods propose using cheaper approaches to generate a short candidate token sequence, which is then verified in parallel by the larger language model, increasing the average matching length and accelerating the decoding process. On the other hand, prompting methods have been used to guide pre-trained language models in generating answers for various tasks, with the aim of improving answer quality. However, the SOT approach focuses on using prompting to improve efficiency rather than answer quality. Section. Limitations. Our current method of assessing the quality of responses has its limitations. These are due to a restricted set of prompts, potential bias from the judges of language model outputs, and the inherent challenges in evaluating the outputs of language models. To improve the reliability of our evaluations, we need to increase the variety of prompts and supplement our language model-based evaluations with human assessments. However, the main focus of this paper is to highlight the potential for improving efficiency. Specifically, we demonstrate that by reconsidering the need for fully sequential decoding in current language models, we can significantly speed up the process. A more comprehensive evaluation of response quality is a task for future research. We believe that the skeleton over text (SOT) approach is conceptually appealing and practical, and our experiments have shown that it can enhance efficiency. However, the current SOT solution still needs improvement. We suggest several areas for future research and pose some open questions. Firstly, the current SOT approach struggles with mathematical questions. This is understandable as there is a contradiction between SOT and the context over text (COT) approach. COT relies on detailed step-by-step reasoning, while SOT aims to outline the main points in advance. SOT is more suited to questions with a clear answer structure that can be planned ahead. To use SOT effectively, we need to develop a system that only activates SOT for suitable question types and descriptions. For instance, if a user asks for a brief answer or a question that requires on-the-spot thinking or reasoning, like solving an equation, we should opt for other generation modes instead of SOT. Secondly, to enhance the SOT capabilities of language models, we could fine-tune them to better comprehend the main points and detailed instructions, and to generate more fluent and natural responses for a broader range of question categories. For instance, fine-tuning could help the model learn to selectively use the SOT mode or revert to one-stage sequential decoding. Lastly, we have only tested SOT with the standard Hugging Face Transformer library so far. It would be interesting to further integrate SOT with existing optimization techniques, inference engines, and serving systems that are designed for high throughput. This could help us fully realize the potential of SOT in improving both throughput and latency. Section summary. The limitations of our current evaluation of answer quality include a limited prompt set, biased LLM judges, and the difficulty of evaluating LLM generations. To improve the evaluation, we need to expand the prompt set and incorporate human evaluation. While our focus is on the efficiency benefits of rethinking the necessity of fully sequential decoding, future work should include a more thorough evaluation of answer quality. Additionally, we suggest directions for future work, such as designing a pipeline to trigger the SOT mode only for suitable question types, fine-tuning LLMs to better understand the skeleton and expanding instructions, and integrating SOT with existing optimization techniques and serving systems. Section. Open questions. We're left with a few unanswered questions. Firstly, our current approach to the skeleton of thought, SOT, solution requires us to decode all points simultaneously, without considering the potential sequential dependencies between these points. A more thoughtful approach might be to arrange these points into a thought graph, where the connections represent these sequential dependencies. This way, the decoding of a specific point could be influenced by the detailed contents of its preceding points. This suggests that we might need to evolve our structure from independent points to a dependency graph of points. Moreover, this structure might need to be dynamic. Think about how we process and write information. We don't just follow established protocols, but we also generate new ideas, discover new information, and identify new connections as we go along. This spontaneous process is crucial for logical reasoning and creative thinking. Therefore, instead of sticking to a static content structure, we foresee the need to guide AI to self-organize its thoughts into a dynamic thought graph, where the thought structure can be adjusted on the fly. This could potentially merge the advantages of the skeleton of thought in terms of efficiency and global thinking with the benefits of the chain of thought in logical reasoning or spontaneous thinking. Secondly, while many efforts to enhance model quality have shifted from focusing on the model itself to focusing on the data, we haven't fully explored the potential of data-centric engineering for efficiency. The skeleton of thought is our first step in this direction. We're excited to see more explorations that will uncover the full potential of data-centric optimization for efficiency, adding a new data layer to the existing technique stack of model software hardware co-design for efficiency. Section summary. The current solution for organizing points in a text ignores sequential dependencies between them, but a better approach would be to create a graph of thoughts, where points are connected by edges representing these dependencies. This dynamic structure could combine the efficiency of a static content skeleton with the benefits of logical reasoning and impromptu thinking. Additionally, while efforts have been made to improve model quality through data-centric engineering, the potential of data-centric optimization for efficiency has not been fully explored, making SOT an initial step in this direction.